Hello, 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 beautiful people. I hope everybody can hear us out there. Can you guys hear us?
I can hear you.
All right, here it comes. Okay, can you guys hear us out there? Sometimes yes, loud and proud. Can you speak? What we're trying to do right now is make sure Dr. Strong, we had to call him from Google Hangouts because he's having trouble with his laptop. So he's going to speak right now, and I need you guys to let me know if you hear him. Hi, Dr. Strong.
Oh, how are you?
Did you guys hear him? Great. Okay. So thanks for tuning in to the live hangout tonight with Dr. Strong. How are you doing this evening, Dr. Strong?
Very well, thank you.
We have Dave in here as well. He has been trying to help us with some tech issues. A little bio here on Dr. Strong. One second. Dr. Strong received his undergraduate degree in astronomy, and he has a PhD in high energy astrophysics from the University of London in 1979. He studied X-ray spectroscopy for his PhD thesis at the Muller Space Science Laboratory. He launched two solar sounding rockets from Woomera. Did I pronounce that correct, Dr. Strong? Woomera,
Boomerang.
Woomera, South Australia. He was briefly an astronaut candidate. Specialties, solar physics, space weather, how solar variability affects the Earth. He worked as a research scientist at Lockheed Martin Advanced Technology Center in Palo Alto, eventually managed the Space Science Division. His group built most of the solar imaging instruments used by NASA and NOAA agencies. For example, SOLMAX, Yoko, the Hinodode. Did I pronounce that correctly? Hinode, Soho, Trace, SDO, Iris, Goes In, and Goes R series. Also, he built the Earth imaging instruments like EPIC and Discover and on the Goes R. He was a NASA advisor and he chaired the NASA Sun-Earth Connection 2000 Roadmap Committee. He has published over 200 peer-reviewed papers and a book, The Many Faces of the Sun. He retired in 2007 and lives in Maryland, in the Maryland suburbs of DC. And as a hobby, he runs a YouTube and Twitter channel, Dr. K. Strong, and debunking pseudoscience in the media. Thank you so much for joining me today, Dr. Strong, to help shed some light on the cycles of the sun and the reality of climate change. So,
Well, for inviting me.
It is. I'm very honored to have you here. So I'm just going to jump right on in. What I have here, I have questions and also claims that I see both on Facebook groups and on YouTube. So first question I have here is, do you believe that the sun can influence the Earth's weather?
Indeed, over the long term, of course it can, because if the sun's intensity changes, the temperature of the Earth will change. For example, over 1 billion years ago, the sun was 30% less intense than it is now. So that's obviously going to change the temperature of the planet.
Correct.
But if you're looking to try to explain the short-term variations like global warming with the sun, I think you're fresh out of luck.
Right, right. Can you guys in the chat see my screen share? I'm hoping everybody can see the screen share. Let me pull up the chat to make sure. Can you guys see the screen share? All right, excellent. Okay. Has the IPCC taken the possibility that the sun has a role in climate change?
Well, there's a lot of people out there that claim that the IPCC has ignored the sun in its various assessments of the climate. That is untrue. Initially, the first couple of IPCC reports were done in the early 90s. They didn't really know very much about the solar variability in the total solar radiance. In fact, my book, The Many Faces of the Sun, was the first book to actually flesh that problem out. But ever since then, the most recent reports have featured quite a lot of information on the sun. In fact, several of my colleagues have actually served on the IPCC panels. Peter Foucault and Judith Lean, for example, were on one panel that I know of. So these are very prominent solar physicists, and their opinions were taken into account. And if you look at the reports, it does in fact mention the sun quite often.
Okay. The sun varies on approximately 11-year cycle. Does the solar cycle influence the weather of Earth?
Yeah, if you could show figure 1 rather than figure 2, that would be helpful.
Here we go. There we go. Can you see it?
I can see figure 2. I can't see figure 1. But anyway, I can make do with this.
I just pulled
there you go.
There you go. Okay.
What I've done here is I've plotted the temperature anomaly for the Earth in that stacked plot. Blue shows below average temperatures, red shows above average temperatures, or the averages for the 20th century. And I've superimposed upon that in green the timings of the solar maxima for cycles 12 through 24. And if you look at that, you can see no particular warming during the periods of solar maximum. Some of them are lower at that time, some of them are higher, just sort of random. So there's no real effect. And if you back off to solar minimum, which is about 3 or 4 years before that, again, you have a similar thing. Some are high, some are low. So there seems to be no particular pattern timing pattern to link the solar cycles with any warming or cooling periods for the planet Earth. But you can check that a second way, and if we could go to figure 2, we can do that. Okay. We can actually compare the sizes of each one of these cycles with the warming. So the largest cycle, which is solar cycle 19, should have the maximum amount of warming, and as you can actually see, it has one of the smallest amounts of warming.
Right.
Some of the smaller cycles, actually, like cycle 24, has the maximum warming. So again, even if you either on timing or amplitude, there seems to be no relationship between the solar cycle and the temperature of the Earth. Okay.
So, okay, can we gauge the size of the solar effect on global temperatures?
It's a very complicated.
Hello?
I'm getting some sort of interference. I'm getting that.
Are you getting that echo again?
I need figure 3. I need figure.
Okay. And you're getting the echo again, aren't you?
Yeah.
Oh, crap.
I'm that's so a technical term.
Yes, that is the technical term I would use for that. Oh, crap. I'm sorry.
Let me see about the problem. Is it giving feedback to the other folks there?
Okay, let me check right quick. Are you guys getting feedback? I think, yes, I think echo, echo, echo. Are you getting a
Has it gone away?
Well, they said
No.
no. Are you still getting it? Everybody says no, they're not getting feedback.
I try to talk without feedback. So if I'm in, that's okay. In figure 3 here, I've
Okay, I have to
raised that the sun's intensity at the surface of the Earth can change. The first one is the total solar radiance, i.e. variations in the sun. So here, shown at the top here in the first figure, there are 3 cycles, and you can see that they're relatively small. They only vary by 0.1% over 11 years.
I'm just trying to
so
zoom it in a little bit here. And it keeps jumping back to that one every time I'm trying to zoom it in. Okay.
Don't bother to zoom it. I think it's okay as it is.
Okay, there we go. I will zoom it back out how it was. And there we go.
Anyway, so the change in total solar radiance is very small compared with the overall cycle. Over a period of a year, the distance between the Earth and the Sun changes because the Earth's orbit is elliptical. In January, it's closest to the Sun, about 147 million kilometers. In July, it's furthest away from the Sun at 153 million kilometers. That creates a 7% change in the total amount of radiation hitting the Earth. It's due to the inverse square law. So that is 65 times larger than the change in total solar radiance over a 10-year period, over 11-year period. So, now, even bigger, consider the seasonal changes. So the altitude of the Sun in the sky varies by 46 degrees over a period of a year. So in summer, when the Sun is high above your head, you're getting a lot more radiation than you are during the winter when the sky. I've done a quick calculation here. Degrees. That would be at Montreal, by the way. The change between summer and winter there, the amount of radiation hitting the planet, that part of the planet, is a factor of about 2.5 or 258%. That effect is 2,300 times larger radiance. You seem to be jumping around on the figures here. I'm not quite sure why.
I'm sorry, okay. I did that. I'm sorry.
But anyway, so you can take a look. If you've got a factor of 2,300, you can take a look at the change in temperature from summer to winter in Montreal, and that's about 30 degrees centigrade, which would imply, when you divide 30 degrees centigrade by 2,300, that the TSI change would be of the order of 0.02 degrees centigrade. Very small indeed. Now, that's a very rough calculation, and you should really do the models properly and all the rest of stuff. That gives you some idea of the order of magnitude. We're not seeing a modulation with the solar cycle. We're not, and when there are much bigger effects around that we hardly notice anyway. So the solar cycle is going to be a very small factor.
So basically, the sun and the climate are moving in different directions.
Well, we'll come to that in a second.
Okay.
All I've established at the moment is that the solar cycle is not affecting Earth's temperatures in any significant way.
Okay.
We can look at if we go to figure 4. That's the next figure. Okay, can we get the next figure?
Yes, and then we have the question that goes with this, I believe. Do you believe that the sun is causing the increase in global temperatures that has been observed over the last 50 to 100 years?
Well, your point is exactly right. If you look at the blue here is a plot of the number over the last 7 solar cycles, and you can see that there's a general downward trend. Now that's it. So that means the sun is getting less active over that period. That's exactly the same period when global warming took off. So they are, in fact, going in opposite directions.
Correct.
This curve would have to be the other way in order to be able to explain global warming, and very steeply, I would might add. And it isn't.
Correct. Okay. Here we had talked about some of the other cycles that people have been talking about. Sarkova has a cycle of 400 years. Casey has a cycle of 200 years. And then there's the Gleisberg cycle of 88 years. We have about 150 years worth of reliable sunspot data. It is hard to, this is a quote from you, it is hard to get a reliable periodicity for an oscillation when you don't have the data stretching over multiple periods, assuming it is cyclic. So
if you show figure 5.
Okay. Can you see it?
Not yet.
It'll get there soon. I think you have a little bit of a lag since you're watching it.
Yeah, this is all the solar cycles that we've had recorded to date, going back to 1750. Really, the only reliable data that we have is from about 1850 onwards. The observations were sparse, and there were arguments about how you should record sunspot number, and different scientists did it in different ways. So there's lots of uncertainty over the first 10 or but so if you look at the arrows below, the G there is the length of the Gleisberg cycle. So we have only really 1.5 Gleisberg cycles of reliable data. So that's very hard to establish a periodicity for that. And then there's a Casey's 206 year, and all he's done there is basically said, yeah, Dalton minimum was 206 years ago, so we're going to go into a new Dalton minimum, so the period must be 206 years. So that doesn't make any sense to me whatsoever.
Yes.
We've had this all sort of thing before. People come up with these various cycles and claim that they've solved the solar variability problem. 10 years ago, we had a young lady called Matsumi Ducati published a series of papers predicting that the next cycle 24 was going to be large, and then we were going to go into a very low cycle for the next 2 or 3 cycles. And of course, cycle 24 was not very large, so her model was wrong. And I think Zarkova has done a similar sort of thing. She's managed to solve for all the previous cycles, but the acid test won't not necessarily be the next cycle, because one of the things they say it's going to get very small. Well, what can happen from a cycle? We've got a small cycle at the moment, 90, with a peak sunspot number of 90. 3 things can happen. It can either the next cycle can go up, it can stay the same, or it can go down. So you have a 1 in 3 chance of being right. That proves nothing.
Right.
In science, you need like a 1 in 100 chance. So after 4 or 5 cycles, we might have an answer, but most of us aren't going to be around after that to prove whether these folks were right or wrong.
That makes it very convenient.
Yeah, of course. And all these alarmist talks, you can go back to 2007, 2006, 2009, and all the same people that are claiming that we're going into a grand solar minimum were claiming back then that solar cycle 24 wouldn't be here, and we would be in a grand solar minimum by now. And some of them were even claiming that we'd be in an ice age by now. Yes. And of course, we've just got the highest temperatures for the last I think 3 years. So that doesn't really make any sense whatsoever to my way of thinking.
Okay, well, you kind of covered some of the grand solar minimum claims here. So let me scroll down a little bit. I was going to talk. Well, when
if you go to figure 6, I can show you how well we did on predicting cycle 24.
Yes. It said, but the forecast is for a grand solar minimum and the onset of an ice age. Will that make a difference? So we were going to discuss the predictions, how it works.
Right. Well, here I've plotted the forecast peak of solar cycle 24 and the amplitude of solar cycle 24 on the same plot, and every one of these little diamonds is one of those projections. The red circle is the actual maximum. You can see very few of us got it right, and so the chances of of 104 predictions, we got basically nobody got it right, and these are the best solar physicists in the world. So from that point of view, we still can't predict what's going to happen in a few years' time, let alone 20 or 30 years down the line. And these folks are just making this up, that we're going into a grand solar minimum. The chances of that are very remote. And even if we did go into a grand solar minimum, it wouldn't cause an ice age.
Right. And you were saying that we were only losing about 0.1% of the incoming radiation.
Well, actually, it's less than that, because that's the peak to peak. That's the variation from the maximum to the minimum. Of course, the average is half of that. So we're losing 0.05% of the radiation if we went into a grand solar minimum. And that is basically negligible. We wouldn't notice that.
Right. Okay. And an interesting issue. Is there any evidence of the Maunder minimum, or can you tell our viewers about the Little Ice Age and the Maunder minimum? Because some people keep thinking that the Maunder minimum was the Little Ice Age. A lot of people don't understand how long it lasted.
Right. A lot of people say, okay, the Maunder minimum occurred when there was ice on the Thames and all the rivers in Europe were frozen and we had no summers and things of that sort. What they don't realize is the Little Ice Age started in 1350 and went on to 1850. The Maunder minimum started in 1640 and went on to 1710. So basically, the only accurate thing scientifically you can say about the Maunder minimum is that it happened to occur during the Little Ice Age. The Little Ice Age started long before it and went on well after it. So so again, you can't make no link. Now, one of the possibilities is that it might have made things slightly cooler during the time of the Maunder minimum. That we can't really tell. However, if you look at a plot of all the reconstructions of the Little Ice Age, the lowest point on there that I think I remember was about 1690, which would be before the Maunder minimum. So again, it doesn't fit.
And there are a lot of studies that have been done that show that the Little Ice Age was started between, I think it was 1275 and 1350 or something like that, where there were volcanoes that erupted. There were major eruptions that happened, and then there were things that fed it, that continued to feed it to make it.
Well, there are several theories of what caused the Little Ice Age, and it's probably a combination of them. One is there was a lot of volcanic activity back then. The second one is that was the time of the Black Death in Europe, and about a third of the population died. And so there was a lot of land that was laid fallow, and trees started to grow there. So there was a lot of agricultural production. Trees started to grow, so that took carbon dioxide out of the atmosphere. That also cooled the planet. The fact that there was a canopy there and not wheat fields and things of that sort. So from that point of view, there's lots of reasons why the Little Ice Age happened, but it basically is a phenomenon of the North Atlantic Basin. If you look at reconstructions like the hockey stick from going back through that time, the Little Ice Age and a lot of the so-called warm periods, the medieval warm periods, just disappear when you take the whole planet into account, rather than just the part of the planet where we were keeping records.
Right. That's something that a lot of people don't understand, that it was not global, was it?
No, it was not.
Okay. Do other stars show similar behavior as the sun?
Yeah, if you go to figure 7, I can show that. Yes, other stars do show solar cycles.
It should pop up for you soon. I'm sure you have a little bit of a lag.
Yeah, okay. But anyway, yes. Studies of stars, in fact, what they do is they look at a couple of lines in the star's spectrum, the H and K lines, and those lines indicate how much magnetic activity there is on the star. And if you measure the amount of change in that flux level, it actually shows you how the cycles of the stars are going. Still not on figure 7 yet.
It should be showing.
You got figures the moment, at least I have.
Let me make sure they guys. Are you guys seeing figure 7? Yep. Okay. Everybody's seeing figure 7. So what it is because you're watching it, you get a little bit of a lag. So you should be seeing it very soon.
Figure you will see that several of the other stars there. The sun, I think, is, if I remember correctly, is the second one in from the top left. Okay. But you see there are other stars there that show modulation rather similar to that of the sun. They are, some of them have longer periods than the sun, some have shorter, some have much bigger cycles than the sun, some have smaller. Now, if you look at the ones on the right, there are a few of them that look fairly flat-lined. And this has been an argument for years that this shows that they are in their own equivalent of Maunder minima. However, recent results think that some of those stars, at least some of those stars, may actually be misclassified and are not the types of stars that would have a solar cycle anyway. So that whether any other stars are in the Maunder minimum, I still think is an open question.
Right, and it's not something that we can exactly know until we have to have a little bit better technology, right?
What you need is more telescope time, because what you need to do this is you need to point a telescope at hundreds and hundreds of stars and measure what these H and K lines are doing in their spectrum day in and day out, and it is very hard to get telescope time to do that sort of study. So they've done it for a few dozen stars, but that's all. So from that point of view, we don't really have enough data to and a long enough period to track whether any of these stars have actually gone into their own Maunder minima. Now, we've had people study isotopes in various ice cores and things of that sort to look for when the sun went into equivalent of Maunder minima. And the average period for that is about 400 years.
Okay.
However, period varies 50 years, about 1,000 years. By saying that the Maunder minimum was 400 years ago, so we're now due for another one, is nonsense. Actually, it could be another 600 years before we get another one of these. So we do not know how to predict these cycles. Now, the work that Zarkova is doing is very interesting and may be a way forward. However, It's not been established yet.
Yes, she's doing some very interesting work, but it needs for more peer review. Is that what you're saying?
Well, we need other people to start doing the same sort of analysis or similar sorts of analyses and see whether it comes out to be the same answer.
Right.
But the problem is it took a very short period of to establish this trend. And as you saw with those solar cycles, we've got a downward trend. So if you take a model that is established on a downward trend, then what you're going to get at the end is going to go to zero. So that's what I think has happened with her study.
Right. Okay, if it's not the sun that has caused the recent increases in global temperatures, then what is it?
Okay, we have three possibilities. If you go to figure 8, first of all, could be a natural phenomenon. It could be the sun, volcanoes, changes in the orbit, etc. It could be human caused. That's the emissions of aerosols, greenhouse gases, and changes in land use. And the last possibility is a combination of the two. And I believe it's exactly that. However, the human sources are the ones that are dominating at the moment, mainly the emission of carbon dioxide and aerosols.
Okay.
So I'm still not seeing figure 8.
Yeah, it's coming up there. I think you just need to give it a minute to show up on your screen.
I think that maybe I should refresh it or something.
No, I don't know if you need to do that. You could do that. You could give it a refresh and just make sure that you mute it.
It came up. Okay.
Okay. And see, so what it does, it gives a little lag. When you're looking at it and you're doing it at the same time, you receive a lag.
Okay, no problem. On the left of this figure, you can see the various contributions to our global temperatures, the inputs. And the dominant factor here is the green line, which is the greenhouse gases. If you look very carefully, there's an orange line there just waving around. That's the solar component. And actually, I think that's a fairly optimistic solar component. You see it's very, very small with the black carbon or the greenhouse gases. The jagged lines are volcanic eruptions. They tend to cool the planet for a period, but very short period, only for a few years. And then you have other aerosols effects that help to cool the planet. So if you put all those together on the right, you can see what the natural things would do, and that is shown in blue here. And you can see if anything, they're slightly down or at least stable. It's only when you add in the human component, that's that pink line, that you actually fit the data that we've got. So it actually seems to require the influence of the carbon dioxide and other greenhouse gases and the aerosols, those are important, to produce the data that we've actually seen over the years.
Okay. Okay, here's another one. But CO2 makes up such a small proportion of the atmosphere. How can it be effective?
Okay, this is a very, can we have the next figure, please? Mm-hmm. This is a very old argument that's been used for many, many years.
Yes, yes.
CO2 only makes up 0.04% of the atmosphere. How can it be making any effect? Well, we can do a little thought experiment if we try. And the issue is it's not how much, what percentage of the atmosphere there's there, it's how much there's there. It's the partial pressure, not the percentage. So you can do a little thought experiment to figure that out. So let's take a volume, a little tube with no gas in it at all, and we'll put in 100 IR photons from the left and shine it through that tube, and guess what? 100 photons come out the other end. Okay, now let's fill that tube with a gas that is transparent to infrared. So you put 100 photons in from the left, and 100 photons will come in from the right. At the moment, there's no greenhouse gases in here. Okay, so next we'll take those transparent gases out and replace them with the greenhouse gas at the same pressure. So there's 100% greenhouse gases in there. We'll put enough greenhouse gases in there that only 50 photons make it through the tube. So 50 come out in the right. So what do you think happens when we mix B and C? We're going to have twice the pressure, and only 50% of the gas is going to be the greenhouse gas. If we put in 100 photons from the left, the transparent gases in there are going to make no difference whatsoever. The greenhouse gases are going to act exactly as they did before because there's exactly the same number of them. So 50 is going to come out the other end. But now you've only got 50% of the atmosphere being greenhouse gases. Now, we could add 4 more lots of the transparent gases there, and you'd have the same effect. You could have 100 times the amount of transparent gases there, and you still have the same effect. So there you'd only have 1% of the atmosphere being greenhouse gases, and you'd still have 100 photons going in the left and 50 photons coming in the right. So it's not the percentage of the atmosphere that is carbon dioxide or any of the other greenhouse gases. It's the partial pressure. How many molecules of carbon dioxide will an infrared photon hit trying to escape from the Earth. Now, the distance for a infrared photon to travel in the Earth's atmosphere at the sea level before it hits the carbon dioxide molecule is about 70 meters.
Okay.
Now, if you and so it hits that carbon dioxide molecule, one of two things can happen. It can be scattered forward or it can be scattered backwards. So after that 70 meters, half of the infrared photons are being hit back towards the Earth. Now, if you had a uniform density atmosphere, the height of the atmosphere would be about 7 kilometers, if I remember correctly. So that's 100 of those 70-kilometer length. So if you take half of the infrared photons out every one for 100 steps, do you know how many photons of infrared will escape the atmosphere without being interfered with by the carbon dioxide? It's one in 1 million trillion trillion. It's 2 to the power of 100, in fact.
Wow.
So very, very few of those photons are going to escape and cool the planet without having to interact with the greenhouse gases. So there's plenty of carbon dioxide there to help keep us warm.
Okay. So I'm very certain that some of my subscribers are going to ask if you could say that in layman's terms.
Okay. Let me think. Basically, the distance that an infrared photon, a heat energy photon can travel is not very far in our atmosphere before it hits the carbon dioxide molecule. If it hits the molecule, it can be scattered. It's got an even chance of being scattered backwards as to being scattered forwards.
Okay.
So imagine how many interactions like that is going to happen. So in order for an infrared photon to escape to cool the planet, it has to bounce around in the atmosphere. In fact, it's called a random walk. So it has thousands of interactions before it can escape. So that keeps it warm. It's like having a blanket.
Right.
So a blanket keeps it warm because it doesn't allow the heat to escape so quickly. And so that's what the greenhouse gases are doing. They're acting as a blanket.
Okay. So, I have another one here. Water vapor is also a greenhouse gas, and there's a lot more of it. So why is CO2 the driver? I think maybe we kind of covered that a little bit. Can you explain to the viewers about the water vapor?
Actually, haven't covered that. The water vapor is indeed a very strong greenhouse gas, and there's a lot more of it. There can be, but the trouble with it is that it's very variable in the atmosphere. You can have 0% of it in the atmosphere, or you can have 4% of it in the atmosphere. And so there's some places where it's not effective at all. There's other places where it's very, very effective indeed. But the point is that the water vapor is a secondary greenhouse gas. And what I mean by that is that the amount of it in the atmosphere depends solely on the temperature, or mainly on the temperature of the atmosphere. So if the atmosphere warms up, you can keep more water vapor in the atmosphere. If the atmosphere cools down, there's less water vapor in the atmosphere. So it acts then to amplify the effects of the other greenhouse gases. So if we have an increase in carbon dioxide, for example, and that heats the planet a little bit, then we'll get a positive feedback because more water vapor will be in the atmosphere, also acting as a greenhouse gas more effectively. And so you'll get more buildup of heat than you would have got just from the increase in carbon dioxide alone. Similarly, if you cooled the temperature a little bit, some of that water vapor would condense out of the atmosphere, so there'd be less greenhouse gases in the atmosphere, and the temperature would drop more than the drop in the carbon dioxide would normally allow.
And CO2 lasts longer than water, correct?
Right. Yeah, the lifetime of water vapor in the atmosphere is approximately hours to days. The lifetime of carbon dioxide in the atmosphere is decades to hundreds of years.
Okay.
So it's more effective for longer.
So if we double the amount of water in the atmosphere, what happens?
It would rain. Simple as that. If you can pump as much water vapor into the atmosphere as you like, and up to the saturation point, and soon as it moves up in the atmosphere, the convective layers will take it up. It will get slightly cooler. It will just rain. Right. So you can pump as much water vapor in the air as you like, and it won't change things because it'll just precipitate out. Now, if you double the amount of carbon dioxide in the atmosphere, that will not precipitate out, and that will increase the amount of increase the temperature, which will increase the amount of water vapor, and so that will increase the temperatures more.
Okay. Why does CO2 control the temperature even though there's less of it?
Because carbon dioxide is well mixed in the atmosphere, up to tens of kilometers above the surface. There's the same proportion of carbon dioxide in the atmosphere. Water vapor, as you go up, as it gets cooler, eventually it condenses and freezes out. So above a certain altitude, which if I remember correctly is something like 7 or 8 kilometers, there is more carbon dioxide in the atmosphere than water vapor. It basically forms clouds and then rains as you go up, or freezes and forms snow as you go up. So the point is that the carbon dioxide will be still there acting as a greenhouse gas well above the altitude that water vapor is no longer effective. And it's the top layers of the atmosphere that determine the cooling, because that's where the infrared radiation escapes into space, and that's what cools the planet. It's all this bouncing around just keeps the planet warm. The only way it can cool is for those infrared photons to reach a place where they can escape to space, and that space that area is controlled by carbon dioxide, methane, ozone, and various other greenhouse gases. But carbon dioxide of those is by far the most abundant.
Okay, there's another idea for a link between solar activity and global temperatures and extreme weather like rain. There's saying that there's more, since we're in a solar minimum, well, they say we're in a grand solar minimum, that there's more particles to form raindrops. They say we have a 19% increase in cosmic rays, highly charged particles, which is causing more rain.
Something like this. As the solar magnetic field weakens towards solar minimum, the protective layer of the solar system, the heliopause, moves in. And so cosmic rays which come from outside the solar system, basically from supernova explosions, can penetrate into the inner solar system more effectively. And that's true. Now, the question is does that produce more clouds? And they've done some experiments at CERN about this, and people have made a lot of fuss about this. However, a couple of things become very apparent. First of all, you've got figure 10 up there, which shows the neutron monitor flux. Now, when a cosmic ray hits the atmosphere, it produces a shower of neutrons. So this is a measure of the amount of cosmic rays coming in. And you can see for the last 60 years, basically, the peak level of cosmic rays has not changed at all. There's a lot of variability, and that's in proportion to the size of the solar cycles. But nonetheless, the overall amount of cosmic rays have not changed very much indeed at all. Now, there's some other problems with this idea. First of all, that the cosmic rays are absorbed very high up in the atmosphere. And that's much above the level where clouds are formed. The CERN experiment has shown that these nucleation centers that the cosmic rays potentially form are very, very small. they have to grow by something like a factor of 100, and there's no mechanism to make them grow. They also have to move lower in the atmosphere to the level where there's some water vapor for them to create the clouds and the raindrops and the ice particles that you want to do to create clouds. And the last part of it is that, yes, clouds, when they form, create a higher albedo, so they cool the planet, which is what these folks seem to want. However, they're ignoring the other side of this, is that the clouds sit over the warm land and keep them warm. You know that a cloudy night, the temperature remains higher than when you've got a starlit night, because the radiation can escape to space more easily with no clouds there. So so the net effect of clouds is relatively small overall. So you can't really say that this is going to produce a major effect. And if the fact that the cosmic rays haven't changed that much, it's not going to produce any effect at all.
And you know, I watched the Jasper Kirkby has some lectures. He has a few videos. I posted a nature podcast. I started back when he first started out in 2011. And I think I have one from 2014 and then 2016. And he himself says that the project will help them sharpen the amount that we will warm. He said it will warm, but this will help us try to find out exactly how much. Well, of course, people are saying that he's been threatened to listen to his old stuff from 2009 or 2011. Don't pay attention to his new stuff. And we all know that's crap. You know, he has himself said that global warming is real and that cosmic rays has nothing to do with any of this ice age and all that kind of stuff. It's more of the misrepresenting the work of scientists is kind of one of the things that deniers like to do.
One thing that might be interesting in the element of cosmic rays is that there's very, very high up, there's something called noctilucent clouds. Mm-hmm. Now, they seem to have changed over the last few years. We're not sure why. Now, there may be some argument that the cosmic rays may be producing those, but at the moment, nobody really knows.
But we also have more equipment for measuring cosmic rays now. We didn't have a long time ago.
Yeah, we have spacecraft that have monitors on board. We have more neutron monitors on the ground. Yeah, so yeah, that is in fact the case.
Yeah, so people will see more information about cosmic rays now. And some might think, okay, I'm seeing all this information, something might be wrong, and that's not true. It is because now the data is starting to come in because of the new satellite missions. Okay.
That's always the danger with new data, but then that it seems to be producing new results, but it's just new data. There was this incident where they said they found the coldest place on Earth in Antarctica. All that was a new measurement in a place that they hadn't measured before. It wasn't that Antarctica had suddenly become that.
Right. Okay. I'd like to discuss a few claims made by deniers over the years. You don't have to go deep into it. What I'm going to do here, I'm going to go ahead and pull up your other graph, so we can have this ready to go. But models are unreliable.
Well, yes. The problem there is they are not often comparing the models with what the models are trying to predict. The first problem with models is, well, there's two issues with models. First of all, you can check whether they are working properly by providing them with all the old data. The amount of sunlight, what's happening with the volcanoes, what's happening with the ENSO cycle, and all the rest of these sorts of things, and then see what temperature they came up with, and does that agree with the observations back at that time? So there's sort of a test there. And most of the models, of course, pass that test. Otherwise, they wouldn't be very useful models. But the problem with the things that they show, they'll often show this hundreds of models all going, diagonally across the page upwards, and then some average of the overall consortium of models, and then show some data that looks completely different from it. And then Figure 11 should show that if you've got Figure 11 available.
Yeah, it should be up. You can't see it?
Not yet, but let me refresh.
Yeah, give it a refresh. Let me make sure
I still got,
everybody else.
10.
Let me see if people are seeing. Are you guys seeing Figure 11? Figure 11 not up yet. Okay. Oh, I know what I need to do. One sec. I'm going to stop sharing. Then go back.
Anyway, what they're basically what they're doing is they're comparing the models of surface temperatures with those taken at high altitudes in the atmosphere. The general trick that they use is to compare the surface models with data from the satellites and the balloons. All often are touted to be much more accurate, and they're not. Satellites don't even measure temperature; they measure microwave irradiance. So they get an effective temperature. Here we go. Yeah.
You see it now?
And so.
Okay. You can see Figure 11. Okay, great.
If you look at these plots there, if you look at these, you can see in blue and green. These are measurements, the data from balloons and satellites. So these are taking temperatures 4, 5, 6 kilometers up in the atmosphere, where we all know it's colder. These models are surface temperatures. And the surface temperatures are determined by interactions between the land and the ocean and the air near it. The satellite measurements and the balloon measurements are taking measurements kilometers up in the atmosphere, where the mechanisms for heating and cooling are completely different. So they're comparing apples and oranges. Now, on the right of that picture, I've got an apples and apples comparison. Here is the precasting effect of the models. And you can see there's the data and compared it with the models, and it looks pretty good. Then you have all these models, and they have different scenarios, because you don't know what is going to happen with volcanoes or the ENSO cycle or any of the other random effects. You can't model what's going to happen precisely. So what you do is you run your model many different times with different assumptions. And so you get a big wide. And so what they do is they say, oh, well, they have 100 models and none of them got it right. Well, they had 100 models because they had 100 different scenarios, and only one of those scenarios, or maybe none of those scenarios, correspond to what actually happened in that period.
Correct.
So the models, if given the right data, will produce the appropriate measurements.
And then
we don't know
we discussed. Go ahead. I'm sorry. Go ahead.
Because we don't know what's going to happen, the models cannot be precise, and so what they do is they do these consortium models where you make all these different assumptions and take the average, and those have been pretty good.
I remember the other day we talked about Mueller. He was a denier, and then he started his own thing. Can you tell the viewers about that?
That was a very interesting case. Mueller out at University of California, Berkeley, was one of the darlings of the denialist community, because he was very critical of the IPCC and the way they did the analysis, and the way the NOAA and NASA and the University of East Anglia did their analyses of the global temperatures. And only comparing the data for while a given instrument was working at a given location. If they change the instrument or change the location, he would start a new time series and compare how the temperatures changed over those shorter periods of time, and then added them all together. He thought that this would give a completely different answer, and in fact, he was even funded to do this by the Koch brothers, who were hoping very much that it would give a different answer. After 3 or 4 years of effort, he came up with exactly the same answer as NOAA, NASA, and the UK Met Office got. And so his conclusion is that indeed global warming was acting exactly as was the other groups had been saying, and that a lot of the predictions, a lot of the critics were exactly wrong. Strangely enough, the Koch brothers then stopped funding him. I can't think why, and of course, so he's now a supporter of the global warming anthropogenic theory, and he is the persona non grata amongst all the denialists.
Yes, and his all this information is free to the public to see. He has the Berkeley Earth stats. He has it all up there. We also talked about how when they thought there was a hiatus, the models were correct, but when the models are showing that it's not, that we're warming, then the models are unreliable.
Well, no. I think actually what they're saying is the data is unreliable. It's not showing what they originally said, that there was this hiatus. So now the data is unreliable. It was really amusing to my way of thinking that this data was just fine while it was showing that there was a pause in global warming, or global warming had slowed. And soon as we got this warming trend from 2010 on to 2016, that actually put the slope right back up where it was before. In fact, maybe even accelerated it somewhat. All the data is suddenly unreliable and been tampered with.
Right.
Very, very hypocritical of them.
Yes. Here's another. Climate sensitivity is low.
Okay. Let me see. Well, you can. It's been measured many different ways, and the results all come out to be about 2 to 4. There's some uncertainties in it, but a lot of the climate denialists claim it's 1. And so doubling the amount of carbon dioxide would only increase temperatures by 1 degree centigrade rather than 2.5 or 3 degrees centigrade. But you can actually do a rough back of the envelope calculation of what the effect is. We know that since records began, that carbon dioxide has increased by about 40%. Since temperature records began, carbon dioxide has increased about 40%. In that time, global temperatures have gone up about 0.9 degrees centigrade. So you can just divide 0.9 by 0.4 and you get 2.5 or 2.25. So that says that the climate sensitivity is about at least 2.25. Okay. Now that's a very rough way of doing it, but nonetheless, it does indicate that it's a lot larger than many of the denialists claim, and pretty much on par with what the IPCC and various other organizations have derived.
What they predicted a while ago is starting to happen. You can see it happen. I saw an article a while back, I think it was way earlier this year, that was saying that there was a model prediction 30 years ago that it is showing that it is coming true. And I think it was about the atmosphere. Okay, I'm gonna.
That was the Hansen model that he presented to Congress, I think, in 1989. He produced 3 different scenarios, A, B, and C. Now, if you take the assumptions that he took and see which of those 3 scenarios was closest to what actually happened in the subsequent years, his model is pretty much spot on, which is sort of ironic because it's a very simple, straightforward model, and it's not too far off from the truth.
Mm-hmm. Okay, glaciers are growing.
Oh, right. Well, I invite anybody just to Google before and after pictures of glaciers and find me one that's growing. The other thing is that they may be lengthening, but the amount of ice in the glaciers are all dropping. And you can see this from some of the results from the GRACE satellite, which measures the mass of ice in the Arctic and Antarctic and in various mountain ranges, and all of those values are going down.
Okay. Sea level rise is exaggerated.
Well, again, they sometimes choose individual tide gauges and say, "Oh, look, this one's going down." The problem with tide gauges is they're hooked to the land, and sometimes land is rising and sometimes land is falling, and so you can get very strange results from individual tide gauges or subsets of tide gauges. You've got to take a large number of them and actually understand what's happening to the land. For example, Scotland, I come from the UK, if you haven't guessed from my lack of accent already, Scotland is rising, is going higher, and the southern part of England, where I come from, is getting lower. So if you have a tide gauge in the south part of England, it's going to say the sea level is rising very fast. If you have one in Scotland, it's going to say that sea level is dropping. So you've got to be very careful. Now, the best way of measuring this is these radar altimeters that are on some of the satellites, and those are showing a fairly steady rise. And in fact, there was a study just published, I've forgotten who did it now, but the rate of rise from 1993 to 2004 was about 2.4 millimeters per decade. The rate from 2005 to the present is 3.5 millimeters per decade. So that's an increase of about 20% over that period in the rate of rise of sea level. Now, whether that will carry on or accelerate, I don't know. We'll have to wait another 10 years to see.
Right, right. Okay, the medieval warm period was warmer. I've already put up the figures, so if you don't see it, you should refresh your screen.
Yeah. We often see the figure that's on the left, which is basically pseudoscience. It's a measure of the temperature in the UK Midlands, which is the longest temperature record anywhere available. You note that it ended at the end of the 20th century. It also was hand-drawn as a matter of interest, based on how people felt that the plot should look. And that would show that the medieval warm period is warmer than now. However, on the right, you can see some of the reconstructions, and those reconstructions have been done from ice cores, tree rings, sediments, stalagmites, boreholes, all sorts of things have been put together to make that reconstruction. You see the different ones depending on what sort of things that they use. And in fact, actually, just a quick aside, you look at the lowest peak in the little ice age there, you can see it's at about 1590, like I said.
Right.
Okay. On the dark line on the right shows the modern temperature record, and you can see that by 2004, which is the last point that they plotted on here, it was already well above the medieval warm period. And I put the 2016 point on this plot, and it's way above the medieval warm period. So that claim that the medieval warm period was warmer is utter nonsense.
Okay. CO2 is plant food.
The idea here is that CO2 helps plants grow bigger. Now, that is true for some plants, in fact, for most plants. However, that's only under very tightly controlled conditions, i.e. you keep the soil moisture at the right level, you add a lot of fertilizers and things to the soil. In reality, okay, so if you do that, then you might get a larger melon than you would have got otherwise when you grow a melon. Now, the problem is that the nutrition in that melon comes from the soil. And unless you put all those chemicals in the soil, the amount of nutrition in that melon is going to be no more than that large melon. It's going to be no more than was in the small melon. So you just have to eat more melon to get the same nutritional value, which is probably not good. Equally, with more carbon dioxide out in the wild, there's nobody to water the trees or the plants or to add fertilizer to them. So they will suffer from other problems, such as because of warming, you're going to have more pests. Weeds grow better in these sorts of circumstances, and also you have droughts and floods that tend to kill off a lot of the plants. So it's in some circumstances it's good for you, good for them, particularly if you do it in a greenhouse. But if you do it out in the wild, or you're expecting nature to thrive, you may be in for a rude awakening.
And then also, the natural cycle adds and removes CO2 to keep a balance. Now, we are producing CO2 without removing it.
Right. That's the problem. Yeah, the oceans emit carbon dioxide. The land and plants and animals emit carbon dioxide, but they also take it in about the same amounts. We emit 9 gigatons of carbon dioxide per year. Now the oceans and land take up a bit of that, so the plants growing a bit larger, and also the oceans becoming more acidic, take out all 4 of those 9 gigatons, but we add those extra 5 gigatons to the atmosphere every year. So although they keep on claiming that we only emit a very small proportion of the carbon dioxide in the atmosphere, what happens is we're keeping adding it again and again and again. And so that's why the concentration of carbon dioxide is increasing.
Right, okay. I have the figure up here. There's no correlation between CO2 and temperature.
Oh yeah, this is a beautiful one. Often the claim is that solar activity is much better correlated with carbon dioxide than temperatures. Now the red plot here is the global temperatures. The yellow plot at the bottom is the solar cycle, and that doesn't look very well correlated to me at all. In fact, as you pointed out earlier, they're going in different directions.
Yes.
And the blue plot is the carbon dioxide, and as you can see, that's rising in lockstep with the global temperatures. So yes, I think basically that old chestnut should be retired, because it just isn't plain true.
Right. This was something that we talked about, and I just really liked your answer to it. CO2 was higher in the past. Would you like to answer it, or can I read your answer?
You can read my answer while I have a sip of tea.
Okay, great, great. CO2 was higher in the past. True. So what? If you like a planet dominated by insects and reptiles, keep on pumping out more CO2. I thought that was it is very true. People do not realize when they talk about that temperature was warmer in the past, they don't realize what was going on during that time.
We've not had CO2 at this high level since humans have walked the earth.
Exactly.
That should be sobering to everybody.
Yes, yes. It really should be, and I don't understand why it's not. Okay, I'm trying to move along as fast as I can here. Are you okay? Or are we?
Yeah, the tea has refreshed me.
Is your wife calling you for dinner?
She growled at me a couple times, but I ignored her.
Tell her we thank her. Volcanoes emit more CO2 than humans.
Oh dear. Yes. This is again an old chestnut that people keep bringing up. The U.S. Geological Survey keeps track of how much carbon dioxide and other gases are emitted by volcanic activity around the planet. And they estimate it is 1% or less of the emissions that humans put out each year. Now, a big eruption may change that, but then again, there may be years with no eruptions that hardly any is put out. So it's an old chestnut. In fact, I think I did a video about this some years ago.
Okay, you have 900 videos on your channel. I actually, I read out your bio, but I also read an introduction of you at somewhere you were speaking at in 2013, And so I have not made it through all your videos, and you have 900 videos on your channel. Okay, we're gonna move along. Okay, but we're seeing record cold. That disproves warming.
Okay, you've put up figure 14. Thank you.
Yes.
All that does is, if the planet warms, all that does is it moves the distribution of temperatures that you see at any given time to warmer. That doesn't mean you won't get any cold temperatures or cool temperatures or even some record temperatures, but record cool temperatures, but you'll get a lot more warm temperatures. And while that imbalance occurs, you know the planet's warming. And on the right here, I've got, for at least for the United States, the relative numbers of record highs and record lows over a period of a decade. And as you can see, for the last 3 decades, there's been more warm records than cold records. And in the last one, it's about a factor of 2 to 1 in the 2000s. So far, this decade is more like running 3 to 1.
I actually saw something from, I think it might have been from the Weather Channel or NOAA or someone, where they were saying, I think it was April or May, they're saying 5 to 1.
Some months, in fact, I think one month it was 7 to 1.
Yeah.
But this is over a decade. So if you integrate it over the 2000s so far, it's something like 3 to 1.
Right.
But in fact, if you look at my Twitter channel, every month I do an update on the number of cold and warm records set during that period. And you can actually go to the NOAA Climate Extremes page, and they will list it for you.
Yes, I also have in the description, I have a great site I'm going to put up. It's a state of the climate, where it tells every month, it tells it for the years. It's got so much on there. I think it's from NOAA, but I do have it saved, and I'm going to put it in the description for everybody to be able to look at, to see for themselves because that's something that these people that are doing this let people know. It's there, it's free. We're not hiding it, we're not charging you for it. It's right there for you to go see. Okay. Spring is not coming earlier. I myself can say that is not true. That is very much not true.
I live in the Washington, D.C. area. I actually was out here in the early 80s, moved to California for a while, and then came back here a few years ago. And the difference in the Cherry Blossom Festival is 2 weeks. From 1980, it was late March, early April, and now it's middle March. In fact, this year, our cherry trees in our front garden were starting to bloom at the beginning of March.
Right.
So that is complete and utter nonsense. And I've seen that pattern all the way around. And one of the things your viewers can do is go to Google and Google planting zones. If you look at the planting zones from about 20 or 30 years ago, comparing with what they are today, and there is a comparison in that set of pictures, you'll see that they've all moved northwards across the United States.
Mm-hmm. Yeah, there's a lot of changes.
In fact, I'm figs in my backyard here in Maryland, which is wasn't possible in the 80s. And one of my neighbors has actually got cacti in her front garden.
Wow.
So that's how much the weather's changed.
Yes, and then the southern half of the United States hasn't had a winter in 2 years. It is, and maybe it may have been longer, but it'll seem like, the fall will come in, and it'll seem like we'll get a little cool spell, and then the temperatures just go above average. Last year in all the way from November all the way through February, we got a little cold in March and April, and that was something that has been cherry picked. There was some snowstorms in June and July, and I went back. I'm a researcher, so I went back, and it has happened before. It is not something that they can contribute to an ice age. But when you look at globally, this is what I try to get people to understand, they say, well, it was unusually, this August that was something I heard a lot about August. It was cool in August, and where I live, that does not account for the rest of the world. Climate change is called global. It's global. It has nothing to do with where you stay at. You have to check out all of it.
You see on YouTube, for example, many people say, "Oh, it's snowed here. It proves that global warming isn't happening." That is, your local weather is not indicative necessarily of global climate trends.
Correct. Okay, I'm gonna since we've been on for a while, I'm gonna skip past some of these, and I'm gonna go on because I sent you some videos of Valentina Zarkova's interview, and I sent you some videos of John Casey, some of interview that he did, and some lectures. I read the book of his, Dark Winter, and I'd like to start discussing that. I think that we basically have covered a lot of evidence for climate change here. And, if we keep talking about what these myths and stuff are, is just a broken record. So,
right.
Well, actually, I think that you covered a part of the interview with Zarkova. But if you could just give your commentary on the video and things that were said.
Well, as I said, Zarkova's work is interesting, but it's not established science yet. So people that are putting it out as though this is now a fact are just deluding themselves and deluding others. We've had, as I said, people before come up with solutions to the prediction of the solar cycle many, many times, and every single time they've been wrong. Now, she may be right for the first time. In fact, actually, I had some ideas very similar to that back about 10 years ago, but it's not established yet, and it will take a lot of work and effort and probably many solar cycles to establish whether she's correct or not. My guess is that she, like all of those before her, are going to come up with the same problems as they did before. I was disappointed. I was very pleased, first of all, that she, when asked, said that she didn't believe in the electric universe. I thought that was good.
Yes.
She believed in classical. I was very disappointed that she fell into the trap of calling the Maunder Minimum equivalent to the Little Ice Age and claiming that all the cold weather back then was due to the Maunder Minimum, which it wasn't, and therefore projecting that if the solar cycle gets into so-called grand minimum, that we will have an ice age, and we certainly will not. So I think on some things she was very shaky scientifically. On the modeling and such like, of course, that's her specialty. It looks very interesting, but again, it's not established as yet.
Correct. Okay. She said that there would be no sunspots, no activity whatsoever, and no active regions, no CMEs.
Right. Well, that's completely wrong. That was one of the things she was shaky on. She doesn't seem to know a great deal about the sun, I'm afraid. We had a mission, I mentioned it earlier, called Yoko, which I had an instrument on, and it took very fast rate movies of the sun in X-rays. Now, we were stunned just how active the so-called quiet sun was when there were no sunspots around. That the sun was still doing, admittedly on much smaller scale and much less energetic scale, but things were changing and continuously everywhere. Bright points were producing little flares. Large-scale reconnection of the large-scale magnetic field was going on in the sun. All sorts of things were happening that we didn't know about until we got this very high cadence. And now with the Solar Dynamics Observatory getting even higher cadence, you can go to look at some of their data, even in the quiet sun, and it's fascinating stuff.
Yes, our sun is very active right now.
Now, the other thing is that she said about coronal mass ejections and sunspots. coronal mass ejections do not necessarily, in fact, rarely come from sunspot regions. They come from filament eruptions. Those are quiet sun features. And you get coronal mass ejections all the way through solar minimum, admittedly at a somewhat lower rate, but nonetheless, they're there. And so, again, she's completely wrong on that. There's no activity around when when you're going to solar minimum. In fact, we're supposed to be most of the way to solar minimum at the moment, and we just had the largest flare of this cycle, and I believe the last one. We had an X9.3 flare, which is twice as large as any flare that we've had so far this cycle, and I think we have to go back to 2004 to have a flare of equivalent size from the sun. And here we are with some days that are almost spotless around on the sun. There's some huge sunspots on the sun at the moment, which we're surprised.
One thing I've noticed that I find to be a little bit deceiving, it really bothers me. There was a video and they showed the sun in 2014, and then they showed the sun now. Well, not exactly right now. It was maybe a month or two back, something like that, when the sun was very, very quiet. Around January, February, March, it was very, very, very few sunspots. And they showed the sun now and the sun in 2014. And that is very deceiving because the sun was in solar maximum in 2014. So when we go into solar, you don't even have to show a solar minimum from now. You can go back to the solar minimum before the maximum and the sun will look like that. That's what the sun looks like at a quiet phase. And they were showing this to say, we're going into a grand, so this proves it. You see how see how it looks. The sun is going into solar hibernation is what John Casey likes to call it. And that is very deceptive.
They ain't seen nothing yet, because when the sun is in solar minimum conditions, normal solar minimum conditions, it can go months without having a single sunspot anywhere.
Right.
And in fact, the previous solar minimum from 2006 to 2010 was the longest and quietest solar minimum that we know about. So from that point of view, doing comparisons like that is just plain silly. I could probably show you a plot from 2014 near solar maximum where the sun would look less busy than it is now. So because the sun is highly variable. Sometimes one half of the sun is just covered with sunspots and the other side is blank. And so there was probably some spotless days back in 2013, 2014, 2015. And there's more of them now, but there's also some very high levels of activity now. And you can pick and choose. It's again, cherry picking data to do something like that.
Yes.
And until you won't know that there's a new cycle. You won't know that you're out of solar maximum until the new cycle starts. Now, one interesting thing that your viewers may not know is that we've already seen the first sunspot from solar cycle 25. It appeared in December of last year, December 21st, if I remember correctly. And it was in the southeast quadrant. It was a nice little sunspot group that appeared, reverse polarity, and that was a solar cycle at high latitude. That was a solar cycle 25. So solar cycle 25 is beginning to start up already. Now we may be several months before we get another small region come up, or it may be a couple of years before. But the regions are beginning to produce. And the fact that it came that early, to my way of thinking, might indicate that the next cycle is going to be larger.
Okay. Get down here because you just covered everything. So I have to right here. The temperature was reduced 1.5 C during the Maunder minimum, but we were already in a little ice age. The global temperatures may, and for us, how much would we have to drop in temperature to get to Maunder minimum temperature?
Well, basically, a Maunder minimum would offset about 10 to 15 years worth of global warming. So if we went into a Maunder minimum now and it lasted to the end of this century, the temperature at the end of this century, assuming we carry on emitting the carbon dioxide at the same rate, would be the same as it would be now if it was 2085. So you're saving 15 years by going into a Maunder minimum. Basically, it makes very little difference at all. So from that point of view, it's not really going to be any effect whatsoever.
Okay.
Or very little effect, I should say.
I'm gonna skip past some of this stuff. All right, let's move on to John Casey's interview. I watched, like I said, I sent you a video of an interview, and then I watched some of his lectures, and I read the book Dark Winter. Upheaval is basically about volcanoes and stuff like that. I'm more interested in what he is trying to say, what is his evidence, since he is the source to most of these people for their Ice Age claims. Then I don't feel the need to go through them. I like to go to the source. Where did this information come from? So
beat me because I know nobody else that knows things of this 206-year cycle. I think he just made that up out of whole cloth. And then he just basically springboards from that, basically saying that if we had a Dalton minimum in the early 19th century, then 260 years later, we're going to have a Dalton minimum in the next 20 or 30 years. And if there's no 206-year period, then that's nonsense. And these periodicities are not exact science anyway. They're made up on very little data. So you can make any claim you like. And the problem is, I'm sure Casey and many of the others, suspicious observers, Piers Corbyn, and Aris Batsoff, all claimed that this current cycle was going to be not there, and it is there. So they just moved it one cycle further out,
right?
And they'll keep doing this. So if 26 appears, they'll just say, "Oh well, we mean 27," and yes. After a time, we've all died, and nobody will remember what they've said.
Yes, in the book Dark Winter, he talks about that. So he says he's a NASA and NOAA. He was a NASA and NOAA scientist. Now, you told me about he has a BS in physics and an MA in management, and you said that PhDs have difficulty becoming NASA scientists.
He wouldn't get a job as a NASA scientist with those qualifications, I can tell you. Now, he may get maybe some sort of management type that manages contracts or something of that sort, but that doesn't make him a NASA scientist.
Right. He has a lot of propaganda. I don't know if I have the picture here, but on one of his lectures, there is a piece of paper in front of the podium that says, "Don't trust the liberal media." Most of everything he says is don't trust the media. He says there's no serious science behind it. It's been falsified. They're in error. And we all know that that's not correct. All that he's saying is incredibly wrong. And then he has press releases that you pay for. Everything has to be paid for from this guy. But I want to go into some of the things that he was saying. We're not seeing. Go ahead.
Media, first of all.
Yes.
In terms of global warming, the media over-reports the negative parts of this, the denialist case. If they were following the actual science, 99% of the reports would be pro-global warming, and less than half of them are. So that's one problem.
That's exactly what they do.
The second area is that a lot of the people that write in the media on these and other issues are not scientists or have no scientific training. I've suffered badly from trying to talk to the media about issues, scientific issues, and then seeing a report that says almost exactly the opposite of what I said. And maybe I'm not clear in what I say, but basically they didn't get the message. I'll tell you a little quick story, very quick story. When I was an astronaut candidate, of course, our local newspaper in Portsmouth in England was very interested, and they interviewed me. I came down there, told them all about the experiment we had on the space shuttle, the T.R.O.L.L helium abundance experiment, CHASE, and what it was doing and all the rest of this sort of stuff. And at the end of the interview took a lot of time. I was describing all the things you had to go through as an astronaut candidate and such like. As I was just about to walk out, he said, "Oh, one final question. What's helium?" So basically, I found out that he was a sports correspondent who had been stuck with this astronaut interview. So he had no expertise in science whatsoever, and he was writing about our British experiment on a space shuttle and the possibility of having a British astronaut on the space shuttle. And he knew nothing about the subject whatsoever. And we come against this a lot because a lot of scientists don't want to be in media. It's mainly English majors and things of that sort that want to, but then they don't know about what science is real and what science isn't. And they can get fooled by this pseudoscience that people like Kerry put out. So you have to be very careful.
Yeah, the media definitely focuses on whatever will get them the most views.
Right, exactly.
And mainly that's negative stuff. You know, it's not about, you know, trying to fix anything, not about any of that. It's just about arguing, and it's about politics. And, you know, there's a comment that was made about you that you were a fake scientist, and that I found the most liberal person that doesn't like Donald Trump. What does the politics and your personal dislike of a man have to do with science? This is science. Science has nothing to do with politics.
I'm with the majority of people that don't like Donald Trump, but nonetheless, I am neither a liberal. Actually, I've voted only conservative in my life. The trouble is, conservatives have lost their minds, so I don't vote anymore.
A lot of scientists have a problem with Donald Trump. A lot. There was a march, for Christ's sake.
Yeah, but what he's doing to science is terrible.
It is an attack.
The whole concept of me not being a real scientist. I invite him to look me up on LinkedIn. I invite him to look me up on ResearchGate and see all the publications I've done, see all the things that our fellow scientists have said I'm qualified for. And yes. I don't expect him to apologize, but he should.
Yes. And John Casey said himself that one of the lectures I watched, they had a Q&A at the end, and they asked how he came up with his RC theory, which is this 206-year cycle.
Right.
And he said that it was from solar proxies and all this stuff. Well, it turns out he was using China as a base. He didn't do this globally. And he also stated right then and there, I did not ask any other scientists for anything. It has not been peer reviewed. It is just it is his predictions and what he thinks. It is not based on science at all.
Yeah, most of these things that they put out on channels like the Grand Solar Minimum and things of that sort would never get past peer review in the first place.
Right.
That's why a lot of the global warming deniers don't publish what they're talking about, except for in a few cases where they've got a magazine run by the oil companies that will publish these things, and then they're not peer reviewed anyway.
Right. They're fake. They're not real. And they have a lot of people have been questioning peer review. And, you know, I asked you about that. Was the peer review process broken? And you said it's fine. It's absolutely fine. It's just that people need to, what I think is people need to make sure what they're reading. When you go to a journal that's supposed to be peer reviewed, check it. There are places you can go to check it.
A peer review process is not understood by many people. A peer review process, you are supposed to check whether they've followed the scientific method, whether they've got clear diagrams, whether they've supplied the data that supports their conclusions. You're not trying to you don't redo the analysis. You don't say, I don't believe this, therefore they can't publish it, or even though there's problems with it, they should publish it. It's actually a very adversarial type of thing, and it's anonymous. You don't know often who's doing what. And so it's a very, very fair process, and it's very annoying. I've just had 2 papers peer reviewed for the Bulletins of the American Meteorological Society. One will be coming out in November. I think the other one will be coming out either in December or January. And it's taken a year of going backwards and forwards with the referees to try and make sure that I've done the things that they said I ought to have done, and I'm not doing things that I think I don't have to do or shouldn't do. So it's a bargaining process,
right.
And it's very adversarial.
Right.
And people don't realize that.
And that's the reason why they don't submit to peer review, because they know that the process is not an easy process. It is just not. Okay. He said, we are not seeing what we were now. These are claims. We have some claims that he made in his recent interviews, which is basically he just says what he said with different dates. He says the same thing, but he says it with different dates. If you read the book Dark Winter, he says that we are not seeing what we were told we would see during winter, which is less snow and much warmer temperatures. Now, he wrote this right before 2011. It was released around 2011. So during these 6 years that have passed, you can see that we are seeing what we were told was going to happen, which is more extreme weather, which is happening, and less snow and warmer temperatures.
Not just that, we've had 5 of the 5 warmest years on record since that book has come out. When he was claiming in that book and some of his other press releases and such like, that we were about to have a major turn down in global temperatures starting in 2011. Okay. And it's done the exact reverse, gone up.
I have an exact quote here. I've taken screenshots of very important things that I wanted to talk about with him, just to quote him. He says, it is important to note from the table, he had a table, that the present 1990 to 2010 warm period will be the last record warm period for the next 206 years until the next bicentennial cycle renews between 2180 and 2211. Now, in his interview recently, he said, we just came out of peak warming in 2015 through 2016 period. This will be the last warm spike for 400 years. So he has just changed the date. If we were supposed to be in the last warm period, then we had what was, I think, was 2009 through 2016 were the 10 warmest years. Well, 1998 to 2016.
Well, the point is that his 2011 prediction was wrong by 2014 because that was the warmest year on record.
Correct.
The 2015 prediction was wrong that year because that became the warmest year on record, and was wrong even further because 2016 became the warmest year on record. Mm-hmm. So we had 3 record warm years in a row, and so consequently his predictions, both predictions, are completely and utterly wrong. And by his own yardstick, once you have a wrong prediction, you don't know what you're talking about. So right. I think we don't know what he's talking about.
Okay, from here, this was on February the 4th, 2011. The SSRC issues press release 2011 showing that the next phase of global cooling has begun, as marked by a record drop in Earth's ocean temperatures. Relying on NASA and NOAA satellite measurements and processed by other government contract organizations, The SSRC press release makes note of how this new record steep drop in ocean temperatures supports its May 10th, 2010 forecast for a record global temperature reduction by December 2012.
Well, nothing that he said there is science.
Exactly.
You can make whatever claims you like, and unless you've published it and it's in writing, and you haven't changed your mind like he seems to have done, that isn't science. You not only got to say you've got to say why you're saying this, how it's relevant, and what's going to happen. And when that prediction comes true, you have to say, "Oh, I'm sorry, my model was wrong, and here's a revision of why I revised it and how I revised it." He's doing none of that stuff. He's just making wild claims that incorrect data that he's putting out is substantiate what he's saying. He's just doing public relations. He's telling lies and trying to get poor people that don't really understand these things to believe what he's saying. And just by repeating it and repeating it and repeating it.
Mm-hmm.
But science, what he's doing, he's just making outlandish claims. Yes. And I'm not remotely interested in what these sort of claims. I think there's a greater likelihood that we're going to go into a grand solar minimum than me reading his book.
Right. Okay, this is something I wanted to discuss because I've seen a couple of people saying this. Only twice in history has a solar cycle had a double peak. That happened in 1910 and in 1790 to 1830. Major cold cycles followed these peaks. That's all we who study solar physics needed to see. This is a direct quote from John Casey. So, Mr. Solar Physicist, what would you say about
being
that?
Amused because I showed that quote to a colleague yesterday.
I talked with her as well.
We couldn't think of a solar cycle that had less than 2 peaks on it. Most of them have 2, 3, some even have 4 peaks in them. And so what he's talking about is utter rubbish.
Mm-hmm.
It's not supported by the data. I can show you plots of the magnetic field for the last 6 cycles, and they've all got multiple humps. I can show you daily sunspot numbers smoothed over a 28-day rotation period of the sun, and there'll be periods of activity, maybe 3 major activity, maybe 3 or 4, sometimes more in a solar cycle. If you do it by hemispheres, there's even more peaks. Mm-hmm. So he is not studying the sun. He is just making stuff up, which, as I say, is not science.
I could go on with this guy's stuff for who knows how long. The concept that mankind's industrial greenhouse gas emission causes climate change has never shown itself to be a reliable predictor of climate change. It has been routinely wrong.
Well, we showed a picture earlier where it was. So
okay.
I think that we can discount right from the very start.
Yep, we already got that one. And that's basically all that I think that we need to cover today. I think that we have covered a wide range of these topics. Can always do it again, maybe one day, who knows.
But if you're going to post this on YouTube and people have questions for me, either post a question on there and I will answer them, or come to my channel, either my YouTube channel or my Twitter channel, and ask questions there, and I'll be happy to respond to them.
Okay, I just looked at the chat and I did forget something. We did say that we would very shortly kind of discuss the electric universe. Mr. Wilbarger, he is pushing the electric universe theory. And oh yes, one thing. Particles, there's more cosmic rays in the atmosphere, more highly charged particles, which are penetrating the core of the planet and warming the planet. Wait, global warming is a fraud, but that is happening, and that's warming the planet. too.
First of all, we showed earlier that there are not more cosmic rays.
Mm-hmm.
They've been constant for about the last 6 years. But secondly, the kind of energy in a cosmic ray in an individual particle is high. But if you add them all up, it's a tiny, tiny amount. In fact, you strike a match and you'd probably have more energy from that match than you would from all the cosmic rays that come in a few seconds. So that's not going to heat any planet. And besides which, cosmic rays are absorbed in the top part of the atmosphere. How do you think cosmic rays are going to get through all the rest of the atmosphere and tons of rock to heat the core of the planet? They're not going to do it.
Right.
Simple as that.
Right.
So,
being
again,
a solar physicist, can you? I'm sorry. Can you kind of just give us a rundown of the electric universe? You know, what are your thoughts on the electric universe?
I assume you're not allowed to swear on this channel, right?
Yes, you are. I am a nerd with attitude. You can swear here.
My best to do because it's very unscientific. No, one of the things that got me about the electric universe, annoyance with the electric universe, is this idea that the sun is not emitting energy as a result of nuclear fusion in the core, but from some outside source of energy as it travels through the galaxy. Electric currents are coming into the sun and warming it and producing the heat that we see. Well, first of all, how do you explain all the neutrinos that are coming from this core of the sun, which are indicative of the nuclear fusion process? Secondly, if there was a huge flux, and it would have to be a very huge flux of energy coming into the sun, why haven't we detected it? If the Earth passed through that flux, we'd be evaporated in a few seconds. And we have spacecraft all around the sun, which should be detecting these things, and we haven't seen it.
Mm-hmm.
So from that view, again, nonsense. Also, they had this theory that comets weren't actually ice and rock and dust, but they were some electric phenomenon. Of course, we've now landed on one of them and found that it's made of ice and rocks and dust.
Mm-hmm.
So again, the electric universe theory falls at the first fence. So I have no respect for the electric universe theory whatsoever.
Correct.
Now, a lot of things in the universe are controlled by magnetic fields and electric currents and electric charge and things of that sort. But that's part of classic physics. Mm-hmm. They're rejecting physics.
Right. And without classic physics, then Einstein's theory, Newton's theory, you know, those theories were used to orbit spacecraft, correct?
Yes, absolutely. Now, one of the things I would like to ask somebody from this, how many lives have been saved so far and will be saved as a result of all this classic physics that's being used to predict where these hurricanes are going to go, and to get people out of the way of them, compared with what the electric universe would be predicting from those same sorts of problems? The answer is we're saving an awful lot of lives with classic physics right now.
Yes, I read a physicist that went to the one of the symposiums, that the conferences that they had with I can't think of his name right now, but he was kind of like they're like the Thunderbolts project.
That's right.
He went there, and he asked them, was there any math or what about their theory would be able to help mankind, would change anything, or, you know, what the math or anything like that? And they said, oh, well, no, you know, we don't have that. And then he said, so what's the point? He said, well, a greater understanding of reality. That is,
well, you know, it's not been verified by any experiment. In fact, all the experiments have verified the classical physics, and so until they come up with something in classical physics that's lacking, that they can explain and explain all the other stuff at the same time, then I'm not going to pay them any attention. But
And science
things
is
that they've come up with
always, go ahead.
about the sun is absolute nonsense.
And science is always looking for advances. That's the way I've always seen it. You know, they act like, you know, all this stuff is hitting, and there's this giant conspiracy of all the scientists and climatologists coming together to make us have a better world. How dare they do that? You know?
Do you have any idea how contentious scientists are? The thought of them being conspiratorial is almost laughable. I think if you put 6 scientists into a room and asked them what day it was, you'd come up with 7 different answers.
Right.
You know, the idea of a conspiracy is laughable.
We've been here before. You know, during history, science has made progress during history. When people were dying of diseases, science comes along, and science has brought us along with technology over the years. There's always one point in time, as you can go back, where science came in and it helped us, and I think that's what's happening right now, that it is time for people to let go of their biases, and understand that what scientists are trying to do, and what we all need to do, is we have to evolve as a species.
I think the issue here is more along the lines that science makes mistakes, but it's self-correcting. Eventually, even when you make a mistake, somebody will come along. Newton came up with some very good laws of motion. They worked for 400 years until Einstein came along and pointed out there was a tiny error in them, and that when you go fast enough, those laws of motion don't work anymore. And somebody will probably come along and point out a problem with Einstein's work at some point in the future, and so on. What I've been doing depended on the people back in the 1950s and the 40s and the 19th century working on the sun. So I was able to do the work that I did during my period. And I'm hoping that other people who come along after me will take my work and take it further. So it's a self-correcting and building process, a constructive process.
Correct.
And so, yes, that's how you get those advances. But the point is that science, unlike most things, is self-correcting.
Yes, it is. Well, I just want to thank you very, very much, Dr. Strong, for joining me. I felt like I knew this was going to be a wonderful interview. Thank you for coming out of retirement for me for a little bit. I really appreciate it. I'm sure all the people watching and the people who are going to watch will be very, very happy to see this. You really, really, really don't know how much this meant to me and my friends.
You're more than welcome. And if people have any questions, just let me know. I'll be happy to answer them.
And I'll make sure that you have the link to this, and you can always chat in the chat box. I'm going to stay on for a second, but I'll talk to you next time, Dr. Strong. Bye. Are you still there, Dave, with me? I don't know if Dave is still here. Hi, chat.
Can you hear me?
Yes. Oh, you have a echo there.
Me?
Yeah.
Okay. Yeah.
I know who's all left here. Thank you guys for staying in here, hanging in here with us for this. I know it's late for some of you guys over there in the UK, especially all you guys in the UK. Uh-oh. Hold on. Wait, I have to hang up.
I see we're still live.
No, I had to hang up my call with Dr. Strong.
Yeah, we're still broadcasting live into the Hangout, though.
Yeah, I know.
Yep.
I know. I was just telling everybody, thanks for joining me and everything. I really, really appreciate you guys coming through here. Share this, guys. Hi, Groot.
That was a great interview. That was fantastic, and covered
Did you enjoy?
very interesting information there, Tiffany. So thank you for setting that up. That was very interesting.
Thank you. Thank you for coming in here and helping me with the tech issues. I'll talk to you guys later on. This will be uploaded as soon as it finished processing. And you guys have a great night. I have to prepare for Hurricane Irma coming up through here to kick my butt.
Stay safe.
I will. Bye.
Good night, everyone.